Okay, so welcome to the second day of the workshop. So it's our pleasure to have Melanie Zeilinger this morning from ETH Zurich, and she will talk about learning in optimization-based control, safety, efficiency, and computation. Thank you.
Thank you so much, Bartholomew. Thank you for the invitation to come here. It's really a great pleasure and honor to speak here. Thank you for getting up on the second day of the workshop and joining us in the morning. So as Bartholomew said, I'm going to talk about learning and optimization-based control. I managed to fit all three words in there. And I'll be coming from a controls point of view, and then we're integrating learning and optimization aspects. So let me begin by thanking the people that have really done the work that I'll be presenting today. Numerous PhD students and postdocs, and of course the entire team. Many of the things that you'll see have come together over quite a few years, and so it's a great team effort. So let's begin by zooming out a bit and look at the motivation. What do we want to do? So we'll be looking at the physical world, and we want to design controllers for autonomous systems. So this will mean that we will not only need a controller that can handle a complex dynamical system, but we will also have to achieve difficult tasks in potentially challenging environments because these systems do not operate in a nice, isolated industrial space. From a controls perspective, that leads to a range of uncertainties that we have to deal with, and we still want to provide some rigorous properties about the controller. So just taking a robust viewpoint, as we do with classical noise and control, will not work because the uncertainties are just too big. So of course, what we know is what has proven to be a promising means to address complexity is learning. So using the information that we see during operation can mitigate the uncertainty. But of course, that sort of often makes it difficult to get the guarantees. So what we will want to achieve, what I'll do in the talk, we'll look at learning a model for a complex dynamical system, an objective, potentially even the constraints, while maintaining guarantees. And I'll focus in particular on safety guarantees. And the approach that we'll be taking is an optimization-based control approach. And so here's a little bit the setup. And luckily, people yesterday have used the same notation, so I don't have to introduce everything. So I'll be denoting the state with X, the input with U. I'll take a potentially nonlinear dynamical system model in discrete time. There's potentially some disturbances or noise, and maybe F can also depend on some parameters that I'm not putting down here. So maybe different from some of the talk yesterday, but was already present in Francesco's talk, is that we do have constraints. So we formulate safety constraints as a set of constraints in the state space, and we call that X. Whereas if you want to think about uncertainty, you could also write that down in a probabilistic form. And then the reason why safety constraints are hard is because we also have input constraints, so we have limited control actions. And then we can write down our optimal control problem. So the ideal controller that we like to achieve is minimizing a cumulative sum of stage costs. We're using our dynamical system model to predict this trajectory forward, and then we can directly impose our constraints. And here we have the potentially infinite task horizon in there. We know that we cannot tractably solve this. We've already seen a successful approximation of that yesterday, and that is model predictive control. So again, I like talking after Francesco's talk because then he will already have introduced this. So we're solving our problem over a shortened horizon. We're taking an approximate cost to go, an approximate constraint set to go, and solve this repeatedly for every measure. And so this is our miniature race car setup in the lab, and you'll see sort of demonstrations of the algorithms here and there using that. So we it's a nice means to demonstrate the algorithms, and luckily also Francesco here has talked a lot about how that model and the problem looks like, so I don't have to introduce it in detail. So I think a reason why model predictive control is also becoming more and more popular overall is because it is tied to optimization, and it's tied to successful optimization methods. So people thought a lot about how to write that problem leverage the structure that we have in such a model predictive control problem, and then it is a range of tools that you can call, and nobody these days actually codes their own MPC solver anymore. And this, of course, makes it extremely convenient today also to use these optimization-based methods. Okay, so that's the setup. That's sort of our tool set that we'll use. And now what I'll do in the talk is I'll go through these 3 topics: learning dynamics, learning objectives, and constraints. But I'll start with introducing our notion of safety and a mechanism of how we can ensure safety. So again, we define safety as constraint satisfaction that we have here, but this is the important part. So we want to be safe for all times, and knowing about dynamical systems, we know that then not every state actually in the constraint set can be safe, because we have the dynamics. So there's actually a subset that we call our safe set, in which we can keep the system safe at all times forward. We commonly define that theoretically with the concept of invariance. So we can easily define a so-called invariant set if we have some autonomous system here as a set in which our state remains for all times. Very intuitive. We can also do that for a control invariance when we have an input and we just put in the existence of a control input at any time point here. So that's great. If we then have such an invariant set or control invariant set, we fit it within our safety constraints, and then we know we get constraint satisfaction at all times. That's a wonderful concept. The holy grail would be to compute such a control invariant set, but of course that's often hard to do, and if we try to do that, the sets might often be rather small and conservative. Now, coming from a predictive control viewpoint, we know that, of course, we can write that control invariance condition also implicitly by writing it as a forward planning problem. So let's say we have some conservative, smaller invariant set or control invariant set. Now we can also say that any state outside of that is still safe if I can find the safe forward trajectory that leads me into that safe set. And I can write that down just as a bunch of conditions as we had it before. So starting at my current state, planning a trajectory forward and ending up in that set. And now my safe set is implicitly defined as a feasible set of those conditions. And that, of course, makes it extremely nice. I just have to solve that problem to check invariance rather than actually explicitly compute that set. So, of course, that's the backbone of all of predictive control theory that we know and why we can prove that we get constraint satisfaction at all times. But you can also use it as a safety mechanism and combine it with other algorithms and policies. There's things like multi-trajectory MPC where this is being used, and of course also in the concept of safety filters. And I want to do a brief excursion into safety filters because this is a topic that we've now thought about for quite a while, and I still think it's a very nice means to augment also other policies, RL policies, etc., with safety guarantees. So I'll briefly talk about the safety filter. What's the idea of the safety filters? I'd say you have some controller that gives you some action. We make no assumptions on that controller. So what we want to do is just have another block here that's the safety filter that takes this input and decides if that is safe to apply to the system. And if that shouldn't be safe, gives us an alternative safe input. So in the literature, that's been addressed with reachability analysis. We have people like Jaime and others here that have worked on this, or also control barrier functions. But now, having seen what I just showed you before, we can also write this as a predictive planning problem to be safe. And I'll focus on this part. If you're interested in the connections between those, we've written recently a tutorial paper in the Control Systems magazine that summarizes this. And if you're at L4DC in a few weeks, there will also be a tutorial on safety filters. But for today, I'll be focusing on the predictive safety filter. So we can directly turn what we just saw before into a safety filter by adding a cost. So now if we're given some input that we want to apply to the system, we can say, well, that input is safe if it leads me to a safe state from which onwards I can find such a trajectory. And so we can have the same conditions as before, and now in order to make this least restrictive, I minimize the deviation from my desired input in some sense. And that already gives me a safety filter. What's nice about it is it's optimization-based, it's scalable, you have this modular component, you don't have to change your policy that you want to apply, but you just add this on top to get the safety guarantees. And of course, we can do extensions to robust, stochastic, etc. models that we're doing all the predictive control theory that we have available. Just to give you one example, so we've also implemented this here in our race car platform. This is a human driver, and the safety filter just makes sure that the car stays on the road, independent of what we're doing. You can also use another policy, you can use a neural network, imitation learning, etc. This is just to show you that it's really independent of which controller you use. What was nice to see is that the PhD student who did this finished, and then he went off to Bosch, and now they have implemented this also on their test vehicle and have run their first tests on the track. So it's a nice concept, but what has always bothered us a little bit, thinking about the safety filter, is two things. It's a feasibility, it's an optimization problem. What happens if that optimization problem is infeasible, then I don't have safety guarantees. And the computation. Of course, you need to solve that optimization problem in addition, and that can be something that people would not like to do. So regarding feasibility, from a predictive control or an optimization viewpoint, you would say, well then, why don't you just relax your constraints? You do soft constraints, so we're adding a slack variable to our constraints, and we're penalizing that in the cost. But of course, we also do know that this does not necessarily lead to the guarantees that we want, because such a soft constraint penalty can just lead to the fact that we're never converging back into a safe set. We cannot prove that with such a formulation. So what we want, of course, is we want a guarantee that if I do start outside my safe set, for some reason I have a large disturbance, I do want to converge back to the safe set, and from then onwards I do get the guarantees that I want. How can we achieve this? Well, this is a property that we do know, say, control barrier functions have. I don't want to go into the details of a control barrier function, but what it is, it's a function, and we define the safe set as zeros up level set of it. But it's important that it's defined beyond the safe set, and it has a decreased property whenever we're outside the safe set, which makes this a stabilizing property so that we get convergence back to the safe set. So can we do that for our safety filter? And so we've done that first in a two-step approach. We're working on getting rid of the two-step approach, but it's easy to think about. So let's take our soft constraint predictive problem, and we first change the cost so that we just minimize the slacks. Right? This is always feasible. I can also always find a slack. Then I take those optimal slacks and I solve my safety filter problem for it, which will then be guaranteed feasible. And what we'll do is we'll use as a terminal condition, as a terminal safe set, we'll use a control barrier function. Now what we can show is that now this optimal cost here can be shown to be a control barrier function. And that's nice, because now I can actually show that this gives me convergence back into my safe set, because I have now, in a sense, a predictive control barrier function. So it's nice because we now get this feasibility guarantee and a convergence guarantee, but it actually also opens up a path towards addressing computation. Because now we have a function available. Before, with the predictive safety filter, that was always a bit of a problem. There was no function. Everything is implicit. But now we have a predictive control barrier function that we can start to approximate, for example. You can do neural network approximations. Of course, you have to make sure that the guarantees are maintained. And this is something that we're now starting to look into, is how we can now also get very efficient approximations of that predictive control barrier function. Okay, so this is a scheme, the safety filter. You can just plug that together with any other control policy. I sort of just wanted to give you a glimpse of that. But of course, what I wanted to sort of convey most importantly, and we'll see that come back later, is this principle of getting safety through planning a backup trajectory. And we'll also use that later on. Okay, so that's the notion of safety that I'll be using. And now I'll start going through the three different topics. And I'll start with learning the dynamics model, because this is also the topic that we've spent most time on so far. And so in the other two parts, on the objective and the constraints, I'll be talking much more about recent work that we've been doing. So dynamics learning, I think, is also in the literature the topic that's mostly looked at. There's different models, of course, that you can learn. I'll be talking about the one that we have most experience with. And that's been quite popular, and this is using a Gaussian process as a dynamics model. Why is that popular? Because you basically have to make no assumptions on that model. You just define a zero mean, potentially, and some covariance function for your Gaussian process. And then you condition on the data that you're seeing, and you're getting a posterior distribution of your dynamics model. So you can, of course, do that and learn just the entire dynamics function, but you can also say I have maybe some nominal model, and then I'm learning an error from it. This is the setup that we mostly use. So it's nice. In particular, we can quantify the uncertainty that we're getting from this model, and so then we can leverage that in the controller design. So this works well. These are some examples, some of which from our own work. We've applied this to high-precision tracking, to autonomous racing. Davide Scaramuzza has picked this up and has also shown this for racing with quad rotors. So these are some promising examples. But I think the reason why we're not seeing this everywhere is that it's still a very expensive problem to solve with the Gaussian process. And so this is what I want to talk about today. So how can we address the computation? The first thing you can do is you can approximate your GP. Right? There's many sparse GP methods that you could use in order to reduce the complexity. But of course, we were thinking, can we not also do something in addition and look at that optimization problem and reduce the complexity of that optimization problem as we've done it in the past for model predictive control? So that will be the first part that I'd like to address. And then in addition to the computational efficiency, if we then use an approximate GP, I also want to think briefly about learning efficiency, because we also want to adapt this model online, and so how can we do that very well? Because if you think about it in experiments, we just don't have lots of data, so we'll be thinking about how we efficiently use it. Okay, but let's start with the optimization side of things. So here's our MPC problem. We're plugging in a GP that makes it a stochastic problem. It's fine. I change my constraints. I make them probabilistic. But really the main challenge is that I now need to propagate that GP forward, and that makes it difficult. I think what's now been established as sort of the most popular approximation is that you take a linearization-based approximation of this. So you can write everything in sort of the mean and the covariance dynamics. Then you get deterministic formulation, also the constraints, and then you can go ahead and solve this nonlinear program. But it's still very expensive to solve. So why? You have lots of optimization variables. You have your covariances in there. You need to take the derivatives of the GP posterior, also the covariance, etc., and that makes it really difficult or expensive to solve. So what we looked at is a tailored SQP formulation that gives us a feasible solution, a suboptimal one though. And we've done that in an EU project that's called ELOX, and we've also been working with Moritz Steele on this topic. So let me briefly show you how it works. So what we're going to do in an SQP step is that we take an inner loop, so we approximate our nonlinear program with a quadratic one, and then sort of iterate to improve the solution estimate. That doesn't help us yet, because that QP is still going to have the same dimension and the same problems. So what can we do in addition? So the trick is, and we've done that in the past as a heuristic, but now thinking about the SQP, you can do that systematically, as we pull out the covariance propagation out of the QP. But we do that in every SQP iteration. So when you look at the problem, then you don't have the covariances, which basically means you're approximating the tightening of your constraints, which is where the covariances come in. But from an optimization viewpoint, you're actually approximating the Jacobian. And so you can relate that to methods in the literature that are called zero-order method. I know in optimization, zero-order methods are something different, but they call it that. And so let's see what it is. So it's a method to approximate the Jacobian, and this has been applied with MPC by Moritz Steele, Andrea Zanelli, and others. And so we realized that we're doing something similar here. So we can apply this step to reduce the complexity. We avoid all the expensive GP computations, and leveraging the theory that they have from those zero-order methods, we can show that we do get a feasible solution, which was not true for the heuristic. And if we have small enough uncertainty, we can maintain the SQP convergence properties. So it's actually now a rigorous sort of grounding of this approach that really makes the GP very simple to solve because you don't have this expensive covariance in there. Show you, give you a sort of a sense of how this works. This is implemented now on the race car. We've worked with them to get a really efficient Arcadis implementation. Here's with the prior GP. We do not have any data, so you see the propagated uncertainty is really big, which makes us operate very close to the center line. So we then just raise basically at the center line, but we can collect data doing this. And then we use that data, put it in our GP, and then you'll see that the uncertainty is reduced. We're still propagating uncertainty to be cautious, and you see that going up every once in a while, and then we get really nice racing performance, and we can also race very quickly. We can solve this extremely fast. So I think we're now at a point where we have a nice way of solving these GP MPC problems, and hopefully we're now looking forward to applying this also to other problems. Okay, so now in the second part, we do want to stick with the parametric GP approximations because we wanted to really make this even cheaper online. And by the way, what I told you, the method, you can also use with the parametric GP approximation. You can not only do that with the complete GP. So now we want to think about the learning efficiency. What do I mean with learning efficiency? There's, of course, different things you can mean. You can think about sort of really the online part and the online data selection, the exploration-exploitation trade-off, dual control, and this is not what I want to address. What we want to think about is how we can leverage data that we've seen from experiments that are somehow related and that we've done in the past in order to adapt our model now quickly when we see a related task. Okay, so we phrased this as a multitask model learning problem. So you're seeing data of different tasks, and then you want to exploit that. You want a model that captures the structure so that you can quickly adapt. And the example that we were using is that of robotic manipulation, because you have different objects, and so the task always slightly changes, but there's some fundamental task structure that remains the same. And so we were working here with the robotic systems lab, and that's also why I wanted to keep that example, because we have a real robotic experiment that I'm going to show you later. And so we looked at a robot. This is a quadrupedal manipulator, so a quadruped with an arm, that has to open a door. And say you've already opened 10 doors, now you see a new door, and you want to quickly adapt to the dynamics of that door. Okay, but before we go into the experiments, I quickly want to tell you how the method works. So again, we want it to be extremely cheap. So there are multitask model learning methods, of course, that rely on neural networks, on GPs, but we wanted to have something that's cheap so we can put it on the robot and run that on board. So we were inspired by these GP approximations, and in particular by the sparse spectrum GP approximations. So what we'll do is we'll rely on a trigonometric basis function formulation that we then use to construct such a multitask model. Okay, so we have M tasks. We take a standard Gaussian measurement model, and now we have a parametric GP approximations with those trigonometric basis functions. We assign a prior distribution to our parameters, and then once we have the data and we have these hyperparameters, then we can directly compute the posterior distribution of the parameters, so the standard Bayesian regression. Okay, how do we make this multitask model? So here the idea is that we say these basis functions, they capture now the structure of the task, whereas the parameters are task specific, so those we will learn online. And of course, you have to think about how to optimize the hyperparameters. We've done that in the CDC paper a couple of years ago. I don't want to talk about that part, but I rather want to show you now how this works for the example that I've mentioned. So here we have the robot example. We do exactly what I described before. We have a nominal model, and then we have an error model. And we'll write that down as this parametric approximation here. And then, so we look at the door opening task, and we say we've collected data from a few runs, and we simulate different doors by attaching different masses to the door. And then we also have a perturbation from a human. Okay, so we have this data, we optimize our hyperparameters, so we get the frequencies and we get the prior distribution of the parameters. So we have our error model, and then we can run online, and then the adaptation of the parameter becomes extremely cheap. You can run a Kalman filter for that. Okay? We're just doing recursive estimation of that parameter. That works really well. So let's first look at the negative example. We're just doing nominal MPC without any online adaptation. It's clear that you cannot achieve the task, so you cannot achieve the desired angle of the door, and you also have very bad disturbance reduction. If you do the multitask learned model, then you nicely adapt, you open the door, and you also reject disturbances very smoothly. Now you could say, well, that's of course just online adaptation. So we also compare it against learning just from one task. And there you can really see that you sort of overfit to the one task that you've seen, and whereas the multitask shows much better performance.
What are the input outputs here?
Oh, okay. So here, so this is basically really just a model for pulling the door. It's a very simple reduced model. It's basically just one.
So it's a force to bend effective.
Yes.
And the output is the angle of the door.
Yeah. Exactly. So we broke it down into, I mean, it looks complicated, but it's actually a very low-dimensional model that we're learning with the GP here. But I think it's an interesting direction to think about now also these multitask model learnings and how we can leverage the data effectively in these models. Okay, so this is, as I said, the part that we spent most time on. Now in the last part of the talk, I want to show you two very recent ideas. And in the first part, I'll in particular mostly pose questions. So, and show you sort of the direction and the main formulation that we've discovered and some first ideas, which really, I think, just opens up also new directions to think about. Okay, so for the first part, we'll now think about the objective. Because if you think about it, of course the dynamics model is important, but if I have a complex task, the objective really specifies the performance that I'm going to achieve. And if I have just a difficult task, it's often hard to sit down and write down a mathematical surrogate model for what I want to actually achieve now with my system. So people have started thinking about this for a while now, and I think the most popular approach is to do Bayesian optimization. So you say this is a black box optimization approach where I have my objective function parameterized, and now I apply Bayesian optimization to find the best parameters giving me the optimal closed-loop performance. We've also applied this. This is, again, the race car. You can easily do that. You have the MPC formulation, you have your parameters, and you run BO to tune the parameters. This is even an extension, so we're doing this with contextual model learning, so that, again, if you have already tuned this for a particular car, and then you're changing the car, then you can very quickly adapt and run your Bayesian optimizer. And so in this case, you're adapting in basically only one iteration. There's, of course, many other things that you could do to tune the parameters. There's sort of preference-based learning. You could do what Francesco talked about. You could learn the cost to go, etc. But there's another option that we had looked at a while back and we now sort of picked up again, and this is the inverse problem. So what's the idea of the inverse problem? We say, well, it's often hard to write down a mathematical surrogate model, but what you often have is a demonstration, maybe somebody that can demonstrate the task, or think about sort of medicine, you're seeing healthy behavior, so you actually do see how the system should operate ideally. And what you want to do is you want to infer the objective from that optimal demonstration. So this is not only addressed in inverse optimal control, but I think even much more prominently in the domain of inverse RL, of course. Both are, in a sense, tackling this problem, yet building on different formulations. So in inverse RL, you'd be starting with your MDP, whereas in inverse optimal control, you're starting based on your optimization problem. The reason why we're going to stick to inverse optimal control is because we're interested in constrained problems where you potentially have an active constraint, and you need to identify that or know that in order to be able to get the right objective. So we're going to formulate our MPC problem again, and we're parameterizing our objective. And now the idea will be that we want to find or estimate the optimal parameters theta from demonstrations that we're seeing. So inverse optimal control, lots of literature, some literature that show that this works well if you get the optimal demonstration. But of course, in practice, you rarely have an optimal demonstration. There's suboptimal demonstrations, there's noise on your demonstration. And that actually would be much, much nicer to address, or that's directly addressed in inverse RL, but actually not in inverse optimal control. So the scope will be that we'd like to now work at the intersection of these two. So we'd like to work with inverse optimal control to take into account the constraints, but also work with suboptimal demonstrations. Okay, so let's take a look at sort of the problem setting and how we could go about doing this. In inverse optimal control, we work with the KKT conditions, the optimality conditions. So let's assume that constraint qualification is there, and so these are necessary conditions. And then you don't need to look at the details, but just we're writing down the stationarity, complementarity slackness, and parallel and dual feasibility as our optimality conditions. And now I'll do a slight reformulation, and you'll see in a moment why I'm doing that. So you can actually rewrite the stationarity condition by pulling out here the parameters and the Lagrange multipliers. And here collecting the Jacobians with respect to u. And then equals to 0 is the stationarity condition. But writing it in this way, you see that it's actually a regression problem where we want to find the parameters for this input-output data, where the output is just equal to 0. So if I now put in the optimal u, I can solve this for the optimal beta. But what if I don't have the optimal u? Well, then clearly, first of all, my stationarity condition is likely going to be violated. I'll also get potential issues with the other constraints, but we're going to skip that for the moment. We'll focus on the stationarity condition. So what is commonly done, then of course people have realized this before in the inverse KKT world. So what's commonly done is you relax the stationarity condition, and you basically solve the least squares problem. Here putting in your suboptimal demonstrations that I'm going to call UD for a demonstration. And then you're keeping your other optimality conditions in the constraints. So that's the classical relaxed inverse KKT approach. Well, why is that potentially not such a good idea? It's because we have errors in the demonstration. We're now thinking about this as a regression problem, and we actually have noise on the independent variable and not on the output. And so that's an error in variables problem, and a least squares estimator is actually not consistent for this. So this was a sort of nice realization, and as I said, this is really just the starting point, that sort of what's been doing in the literature is not sort of consistent. What you should be looking at instead is an error in variable regression approach. And we now have a first paper at L4DC that's going to be presented in a few weeks. So we started to look at different ideas for error in variable regression. So we're modeling the uncertain demonstration as the optimal one plus noise. And now we're looking at different formulations. One is we're assuming that the noise is zero mean Gaussian, and the other one is we don't know anything about the distribution. And so we can look at different techniques. So if you're assuming it's zero mean Gaussian, but we don't assume that we know the distribution. We just assume it's Gaussian. Because if it's Gaussian, you can take a complete Bayesian approach. You basically write this as a map estimation problem. So you want to minimize the negative logarithm of the posterior. In order to do that, we're estimating the distribution of the demonstration with sampling. And then you can start solving this to get an estimate of the parameters. If you don't know anything about the distribution, that's of course not possible. Here you can use an approach based on the total least squares, so you're basically just minimizing the squared sum of the residuals, and then we're iteratively estimating the noise distribution from data. So again, in no case we're assuming that we do know the noise distribution, but we're always trying to also estimate that from the data. We've done a number of examples. I'm just going to show you one. And of course, what we're getting is that these approaches, because they're error and variables regression problems, they're consistent, we're reflecting the quality of the estimate, and we do then add the remaining KKT conditions back into the constraints. So we've changed the inverse KKT approach to have a better objective, but we still have these other optimality conditions in the constraints. So unfortunately, we haven't changed the difficulty of solving that problem, because that's still a really hard problem to solve, and I'd be very happy to talk with the optimization colleagues, and if they have ideas of if there's any hope that we can solve these problems in a better way, because of course that's really hard to do. Okay, just to show you one example, because we've looked at the car so much. This is the nonlinear kinematic model of the bicycle model of the car. And say we want to control the car to some target point, so we're taking the basis functions to reflect that, and then we want to find the parameters, and we can here see that with just the KKT approach, not knowing that we actually have noise on the demonstrations and we have different noise levels, we're not getting a very good estimate of the optimal parameters. That's the root mean square error, whereas with the error and variables approach, we're getting a very nice estimate. And this is particularly an example where we believe that the constraint, the active constraint, is actually important to get the right parameters. Okay, so that brings us to the point where we talked about the dynamics. We've talked a little bit about the problem of the objective, and at least phrasing the problem with some first ideas. But in all of these, I've assumed that I know the constraints. Now, of course, if you're now operating in an unknown environment, you do not know necessarily what the constraints are, but you actually have to go around and also learn about the constraint. And so here's some first results where we're trying to do this, and this is joint work with Andreas Krause at ETH. So what's the setup? We'll now assume that the dynamics model is known, so that is not too hard. We know some of the constraints, so we know the input constraints and potentially some other constraints on the state, and now there's a constraint that we don't know, and we model that with the function q of x. We're saying the constraint is defined by q of x either equal to 0, but we don't know q. And so what we want to achieve is that we get now safe domain exploration in finite time. That's going to be the objective that we'd like to achieve. Okay, so without any assumptions, that's of course a hopeless problem, because if I make no assumptions, I cannot know about the safety of a neighboring state. So I do have to make some assumptions. And of course, that's not an entirely new question. So people have thought about this in sort of, I think, the non-dynamical case mostly. For example, in safe Bayesian optimization. And there the idea is, or the trick is, that one models this unknown constraint with a Gaussian process. So we'll assume that that constraint function has a certain regularity, so it can be modeled with the Gaussian process. And then we can leverage sort of the confidence bounds from the Gaussian process to get some high probability upper and lower bounds on that function. So for us, thinking about safe sets, In particular, the lower bound is important because that will give us a pessimistic approximation of our constraint set, in which we then know with high probability we're not violating our constraints. And so this is what we will work with in order to ensure safety. We're also getting, of course, the optimistic set, which is sort of what we hope to achieve. That is from the upper bound. Okay, so that's the setup. That's how we model the constraint. Now, how do we sample? So we're taking noisy samples, so we cannot hope to learn this fully, but we're assume we're learning it up to absolute precision. And then our sampling strategy is that we're going to find a point that has larger than epsilon uncertainty, and that's in the pessimistic set, so within the constraints, and that is how we're going to sample. So note here, this is just a sampling. We're not thinking about the dynamics yet, so we can relate to the results from the literature that are not necessarily for dynamical systems and extend those to show that there exists a finite number of samples in which we will achieve this. Okay. But then we do want to think about dynamical systems that are non-trivial. So dynamical systems were considered in the literature, but very simple dynamics, like going back, forth, left, right, so in these grid-based worlds. But we want to take some non-trivial, nonlinear dynamics. So how do we achieve safety there? And so at the beginning, we already talked about this. So just saying we're in the pessimistic set is not enough for a dynamical system because not every state in the constraint is safe. So here we're bringing back this idea. Sorry, and I wanted to mention that here, so you just have to sample such that the uncertainty is at least epsilon, but you do not need to sample at the maximum uncertainty, and so you leave room for an exploration strategy here. Okay, so how do we get safety? And here we're going to bring back that idea of planning to achieve safety. So we have our set X, and we have a safe set that we do want to keep the system within. And so to start with, I'll assume that I have some safe set to start with. That can be just a singleton, just the point where I'm currently at, and I know that's where I'm going to be safe. So how do I now choose a safe sampling point? A safe sampling point is where that I can reach from my current safe set while remaining within the constraints, and that's important, being able to return to the safe set, because otherwise it's not necessarily safe for all times. So we'll call that a reachable, returnable set to get the complete safety guarantee. So we have to reach and return while remaining in the constraints. We don't know the constraints, so we'll do that with the pessimistic set. Of course, again, we don't want to compute that reachable, returnable set, so we're going to write that as an optimization problem, exactly the same way as we've done it before. Apologies, that's continuous time, but implementation would then again be in discrete time. It's the same thing that we've seen before. So we want to start in the safe set, return to the safe set. We're going to sample at an informative location while being within the pessimistic set, satisfying all the other constraints. And that gives us the algorithm. So what do? We start with an initial safe set. We have the pessimistic approximation of the reachable, returnable set. So we're solving that optimization problem that I just showed you. We're getting the sampling location. We go there, we sample, we return, we update the GP. That tends to grow the pessimistic set, shrink the optimistic set. We compute the next sampling location. We go there, sample, return, and continue. So we can extend the finite time guarantees because we're now sampling in a subset of the pessimistic set. We're safe because that's the reachable, returnable idea that I showed you. And you can also show that we're guaranteeing that we're exploring the domain. But for this, you need to make an assumption on the dynamics. There needs to be a locally controllable linear system because we need to be able to go to the boundary and come back in order to sample. We can do extensions. You can think about taking, if you know Lipschitz continuity, you can use that to improve the pessimistic set. You can just instead of just doing exploration, you can do goal-directed exploration. You're trying to achieve some goal. And I think the most important one, we can extend this to a receding horizon formulation in order to make it more efficient. So what does that mean? Now, we again start, and now we have some goal that we want to achieve. We have the pessimistic set and the optimistic set. The goal lies in the optimistic set. Now we want to solve our optimization problem that I write here in compact form. So we want to find an informative sample while remaining in the reachable returnable set, and we want to get as close as possible to a goal. So we're going to pick that sampling location, but rather than going back, we're going to start replanning from the sampling location. So we're directly updating the GP. We can expand the pessimistic set. We're going to choose the new location, and so we're directly exploring. And we can prove that actually we maintain the guarantees that I've just shown you before. Here's just a quick example. That's again the car. Here's your goal that you want to achieve. This is a complicated constraint that we don't know. Here we do grow the safe set rather than just keeping it fixed to make the algorithm even better. And you can see that we just slowly sort of explore the domain until we reach the goal. And the yellow one is this optimistic goal that we continue to recompute. Okay, so that brings me to the end. So what I wanted to convey is ideas to address this problem for complex dynamics, constraints, and objectives that we'd like to address to advance autonomous systems. I've shown you an idea for writing safety through this implicit planning problem that I think is sort of a powerful idea that you can use in various different ways. Briefly talked about the safety filter and the predictive control barrier function that you can use for any control policy. We've looked at learning dynamics models with GPs and tailored optimization, as well as multitask learning. Some first ideas on inverse optimal control under suboptimality and how you could formulate that problem, and then at the end, a first approach to also explore unknown constraints. And of course, at the end, somehow we need to bring all of this together. With that, I'd like to thank you for your attention. Of course, all people that have funded this, and happy to answer your questions.